Good morning, everybody. So today we will begin our discussion. This will be the last little bit of our math background. So after today, we will start with chapter 2. Okay. So today we will discuss three things. First of all, I will introduce something that's called a separation vector, or when we do electrostatics, we call something as a script R or a curly R. I'm going to start by representing a vector in the Cartesian coordinates, and then we'll also discuss different kind of other choice of coordinates, cylindrical and spherical. And lastly, we will spend most majority of our time talking about a math function that's called the Dirac delta function, and how we can use this function to help us represent some physical quantities in electrostatics. Okay. All right. So first of all, let's simply draw a Cartesian coordinate. So I have the x, y, and z here. Okay. And I have a vector r. Okay. So how do I represent vector r using x hat, y hat, and z hat? So vector r is equal to something x hat, something y hat, and something z hat, right? So how do I represent this vector r? You're muted.
I think his mic isn't working.
Okay. I can hear you.
I could use Rx, Ry, and Rz.
Yeah, the r and the x component. Now, in the Cartesian, is simply is just going to be here is just x, y, and z. Okay, so it's just going to be x, x hat, y hat, and z, z hat. That is the Cartesian that we use a lot. Of course, the magnitude of r, simply we just write r without vector. Is going to be square root of x squared plus y squared plus z squared. Now, sometimes we use r hat to represent the direction without a magnitude, right? So you want the vector r, but you only want to pick out the direction. So what we need to do is divide the vector r by what quantity?
The magnitude.
Magnitude r, very good. So you get rid of the length, you just have a dimension, sort of the unit of 1. So you end up with x hat plus y hat plus z hat and divided by the magnitude of r. So that's r hat. We also have something called a separation vector describing the separation between two vectors. So imagine instead of having r, just one r, I have r1 and r2, right? I have r1 and r2 right here, two vectors. And I define a curly r, r1, 2, to be a separation vector between 1 and 2. So how are these three vectors related? I will have you guys vote on this one. I don't think we need to go to the breakout rooms, but I will just let you vote. If you want to talk to people, feel free to chat and or use the chat window if you like. Okay, so we have majority of the vote coming in, 42 out of 45. Just a few more seconds to wrap up. Okay, any last minute vote before I close it? Okay, now I'm going to end poll. And let's take a look. All right, tied between A and B, and C got the majority of the vote. Let's take a look. So can anybody tell me what method do they use to figure out the relationships? We see these different vectors. We know about vector addition, right? So when we add two vectors, there's a common method that we use. We learned in intro physics. And what is that method?
You put like the end of one onto the top of the other one. Yeah. Head to tail.
Yes, the head to tail method. So so the simplest way right here is just by looking at which vectors and which other vectors are connected in the head to tail way. So we can start from there. So in this case, the head of R1 right here is connected to the tail of our script R 1, 2. So I know from head to tail method, these two are adding up. R1 plus R1, 2 is going to give me the third one. That is the R2 right here. So you can see that if you simply just rearrange it, you get the C, which is the correct answer. Very good. Another thing that might help you to remember which way that R12 is pointing at is it's from 1 to 2, okay? It's pointing from 1 to 2, so the arrow is pointing this way, not the other way around. And the other way around, you would represent it using R21. So for example, you probably have seen this in your introductory 1520 or 133. That's our Coulomb's law, right? Coulomb's law is saying that the force acting by charge 1 on charge 2 can be represented by using this constant Q1 times Q2, the charge is divided by the distance squared, and the direction is R12 hat. Okay, so which one of these arrows, or more than one of these arrows, or maybe none of them, can represent this R12? Is it A or B or C, or we cannot decide. So again, I'll let you vote, and this should also be a quick vote, okay? So one way might be helpful is to think about the direction of Coulomb's law. If you have two positive, you can pretend it's two positive charges to see which way the force should be pointing at. That might help you with figuring out the direction. Let's go for 10 more seconds. So for those of you who haven't voted, please put it in. Okay, so I get majority of the votes now. Any last minute vote before I turn it off? Okay, let's take a look at our results. So we, yes, so we have majority voted for A, although we are pretty tied for a lot of these answers. E says we can't really decide this curly R unless we know the charge is positive or negative. And B also is majority, a lot of a vote. And C and D. So, okay, so let's take a look this together. In fact, A and C are pointing in the same direction, right? So in the sense that we want, here we simply just wanted to represent the direction as in our curly R1, 2, so it's R hat. So does it really matter how long we draw our arrow? Did I ever mention that you have to draw this vector in this manner? How long is it? I haven't said anything about the length. It's a unit vector, and all we care is you want to indicate to people the direction. So as long as you indicate the direction, A and C simply all indicating in the same direction as in pointing to the right. Right? You're simply just moving A a little bit to the right-hand side. That becomes C. So A and C are not two different vectors. Either they're both correct or they're both wrong. Okay. And now let's think about whether we need to know Q1 and Q2 being same or opposite sign of charges. So here previously we said R12 needs to be pointing from 1 to 2. So let's say you have these two charges, they both have a position, right? Let's say this is R1, the position of charge 1. This one has an R2. So just by what we did before, R12 must be pointing from 1 to 2. So this must be R12 hat. So in the case that A and C are both correct, and somehow it does not matter if the sign charges are both positive or they're both negative, or maybe one of them positive or negative. So let's just see if that works out. If I have a positive charge here and I have another positive charge here, Q1 and Q2, we would say the Coulomb's law by 1 on 2 is, in this case, is Q1 repelling Q2 or attracting Q2?
Repel.
Repel. So it's trying to push Q2 away, right? So the force must be this way. And I know that, okay, then Q1, Q2 are both positive, R12 pointing to the right. It works. Now let's try a different way to see if this notation still stands. Let's say I have two negative ones. So in this case, the force from 1 to 2 is it still pointing to the right, or does it change direction now?
Stay the same. Still
the same, it's still repelling, doesn't matter. Now the only thing that may change the direction is I flip one of them to be a positive charge. In this case, they attract. The force has to be pointing to the left. And you wonder, in this case, is my R12 still pointing to the right? What do you think? Are we still representing R12 to be pointing to the right? Now you can see that we want our force to be pointing to the left. So this force and this R12, they need a negative sign. And do we have that negative sign somewhere in our expression?
You do, but there's a negative sign that comes with the negative charge.
Yes, yes. So it doesn't really matter Q1, Q2, whether one of them is positive or two of them are positive or both negative. You simply just keep them the way it is, and they will take care of the signs for you. If there's a negative charge, then your R12 will flip direction, so that your R12 hat is always simply, in this case, pointing from 1 to 2, regardless of the charges that they carry. And in this case, both A is correct and C is correct. So we will choose D because more than one of these is correct. Okay. So that is simply just talking about how do we represent this separation vector. If I may show you a different way that we write this separation vector, and is instead of treating there are two charges. A lot of times we're treating a source charge and a source charge point in space and a field point in space. And we represent them using R prime and R. The prime is always the source. So for example, if I have some source here, here is my source. There's some charge here. And I will represent the location of that source to be R prime vector. Now I want to evaluate what is the E field here in space. I will represent the point of interest in space to be a field point. And I use R to represent it. So, and then we would define, okay, from the source to the field where you want to evaluate electric field, and there's the separation vector that is called script R or curly R. It's a vector, so R, curly R vector is going to be, you can see it's going to be the combination of R and R prime. So my question for you is, so how do you represent R, curly R using R and R prime? Is it going to be R plus R prime, or R minus R prime, or R prime minus R? It gotta be one of these, so which one?
R minus R prime?
I'm sorry, which one?
Was it R minus R prime? Or?
Yes, it is R minus R prime. Very good. So again, think about this. Where you see where I'm drawing it is from one point to another. Okay, so from the source to the point of interest. And as we practiced earlier, this vector, you can see that R prime, curly R, and R. R prime and R, curly R add up to be the vector R. So R, curly R is R minus R prime. The way that I write this curly R is really dramatic way. Some people don't write it this way, they write their R like that. You can write it however you want, but I just wanted to show that this is not of R, but it's the curly or script R, so I just use this dramatic notation. So when you see this, I want you to recognize that that's what I mean. Okay, so of course we can calculate the R by expressing it in the Cartesian coordinates. So simply it follows R minus R prime, and R we already wrote it is X hat, Y hat, and Z hat. Now R prime is going to be, everything is primed, so X prime X hat, Y prime Y hat, and Z prime Z hat. So you combine them, they become X minus X prime in the X hat direction, Y minus Y prime in the Y hat direction, and Z minus Z hat in the Z direction. So that is your curly R. You can write the curly R hat by simply divide that by its magnitude. And the magnitude, of course, I'm not going to write everything out, but you know how to calculate it. The script R magnitude is going to be, again, is just going to be every of the component, each of the components squared, and you add them together and taking the square root of that. So that's going to be the magnitude of R. We're going to use script R a lot when we do calculation for electrostatics. So just wanted to introduce it here. Okay, second of all, now let's take a look at two other choice of coordinates. One of them is the cylindrical. This one is fairly straightforward. I'm not going to spend too much time on it. The spherical one, we want to spend a little more time to practice. For, we all know that you all know the polar, right? For representing, instead of X and Y, you're representing using R and theta. You're very comfortable and familiar with the polar coordinates. Now, cylindrical is simply adding a z-axis on it, right? So, so instead of everything on the plane, a circle on the plane, you simply just have a z component. So here you have something in space, this point that you're interested in. And instead of representing it using x and y and z in Cartesian, here we represent it using s and theta and z. Polar, we do this in R, but here in our notation, Griffiths, we use S. So S is this quantity right here, and theta is the angle, and Z is still the Z, is how far above the Z axis. So you can see that simply the limits for these are S can go from 0 to infinity, theta go from 0 to 2 pi, and Z can go from negative infinity to infinity. And of course, you will have S hat, theta hat, and Z hat direction. Okay, so let's talk about the direction of these hats. In what direction is S hat?
It's in the r hat direction.
Yeah, it is exactly in your radial direction, so S hat. In what direction is theta hat?
It's in the,
It's pointing clockwise with the sphere, sorry, the circle.
Yes, so always sort of perpendicular or tangential to the point that you're looking at. So yes, theta hat. Now, if I choose two different points, you can see at each different point, the theta hat direction, S hat direction will both change. But at this particular point, that's how I represent it. And the Z hat?
just points in the Z direction.
Yes, pointing in the positive Z direction. Very good. So that's simply our cylindrical coordinates. You can see that's straightforward if we already know how to do the polar. The spherical one, though, is a little bit more complicated, but we can break it down and look at it one by one. I will have a better graph later on to show you. It's better than my hand drawing graph, but here, when we try to work it together, I'm gonna start drawing it. Okay, so in cylindrical, I still label it X, Y, Z just so that we can relate it to the Cartesian if we need to. But imagine that if we're representing, you have a big sphere right here we're working with. So here we have a point again in space. And imagine this is really just a point on the balloon. Sort of you have a big sphere going around. We have sphere going around, and we have a point. Simply imagine this is a round balloon, and this is just a point in the balloon, in the surface of the balloon. Again, we will define and tell people the location of this point by using three variables. One is how far it is away from the center. How big sort of your balloon is, that's R. Okay. Now you also tell people about the location of this point by telling people how far it is away from the Z-axis, and that's theta. And there is a third variable in order to define this point. And what would that third variable be?
Phi or phi?
Phi, yes, very good. It's telling me, well, if I simply project this point on the XY plane, and this projection is making an angle relative to my x-axis with angle phi. So having these three variables, you can decide the location of this point. So now it's also three variables. Instead of x, y, z, now it's r, theta, and phi. So for r, is radial direction. It is radially outward. Now let's look at r hat. R hat is easy to figure out, right? It's simply pointing in the radial direction. So this is my R hat, pointing outward. It's the same line as my R. Sorry, I curved a little, but it's the same line as my R. And what about theta hat? How do I represent theta hat? So this is my Z, and theta is the angle making relative down from the Z axis. So you can see theta is kind of changing its direction in this way. Okay, so what is theta hat? So if I swing a big circle with my R, my theta actually has to be always perpendicular and tangential to my R. So how do I draw the theta hat?
Tangential to the R hat?
Yes, and this way, downward. Okay, now phi hat. How do I draw my phi hat?
Phi hat perpendicular to S hat.
Yes, and this is my S. I want to call this something, I can call it S, and S is related to R. Although S, the variable doesn't enter the picture here. But yes, phi is on the XY plane and is always perpendicular to my S hat. And you can see this is my S. So phi is this direction, phi hat. But I wanted to move everything up to be in the same point, right? So I'm gonna move my phi hat parallelly and move it upward so I can draw everything together. Sort of move it up parallelly, so it's gonna be phi hat like that. Okay. All right, so that's everything.
Dr. Ryan, is this the convention you're going to be following in your class?
Yes.
Okay.
Radially outward, theta hat. Also, R hat is the angle down from Z, and this is the polar angle. Phi hat is the angle around from the X, and that is the azimuthal angle. Sorry. Now let's look at how each of these variables can change. R could change from 0 to infinity, right? Now theta could change. No, let's not talk about theta. We talk about phi first. So what are the limits for phi going around in the XY plane?
0 to 2 pi?
Yes, 0 to 2 pi. Now what about theta?
0 to pi.
Theta to pi. It doesn't need to go from 0 to 2 pi because we have the phi to cover that. If you counted theta from 0 to 2 pi, you will actually be counting every point one more time. So there's no need to. These limits cover up the entire space we need to look at. So that's the spherical coordinates. There is an activity I want you to do later at home. It's actually a physical activity. You have to stand up. Imagine you are a point here in space. You can use your head or your shoulder as the location of that point, and you define a origin somewhere at the corner of your room. And there must be a R hat, theta hat, and phi hat at the location of your shoulder. So you try to point in the direction of R hat, theta hat, and phi hat. This way is very good. It forces us to think about exactly where the hat pointing at. If you can do it physically with your hand, then there should be no confusion when you need to do it on paper. So that is a practice we used to do in class, but we can't really have everybody have the same corner right now, so it wouldn't make sense to compare. But I leave that on the slides. You can go ahead and practice that when you are by yourself, or if you collaborate with another friend. So in the, let's take a look at this. Here we have a spherical element. there's the area dA1. Now, what is dA1? dA1 is simply exactly a patch on the balloon. Think about you're blowing up a balloon, and dA1 is simply on the surface of the balloon. dA2 is in the XY plane. It's a flat area vector. So, can you write out how do we represent these area element dA1 and dA2 in the spherical coordinates? So if you have a piece of paper with you right now, we can try to write it on our paper and we'll work together in class. So let me try to put a few things here on this on the graph. So you can see the area, when we are working with a small enough area, the area is simply, you can treat it as a rectangle. So it's just gonna be one side times the length of the other side, give me the area. So all I need to know is what is the side here and what is the side here? And I can just combine them, multiply them together, I get dA1, right? So let's say the change from here to here is so small. I'm gonna say this is with a length of r. And here, while you're going down, and this is theta. And while you're going, swing it downward, I have a change of angle of d theta, because it's so small, right? The change of angle is also small. So I wanna be able to represent dA1. So actually I'm on to, let me not look at this one. So this is a projection of this point here. And this point has a projection on the XY plane here. Okay, so this is a projection, which means this green line is the same length as what I need here. And you can see this is d phi. Okay, so the area A1 needs to be one side times another. So let's work with the one that is easier to look at. How about we look at this line? Can you guys take a look at the diagram that I draw? Tell me, how do I represent the length of this sort of arc length? If I know what r is, and if I know what theta and d theta is,
R d theta.
yes, r d theta is an arc length, very good. So this is r, this is d theta, and this is arc that I need is simply going to be r d theta. This one I figure out is r d theta. Now I need this one. Now this one is the same as this one. So it's another arc length on the XY plane. So how do I represent the other arc length?
R d phi.
R d phi, yes, we have d phi, but this is not r anymore. This is a projection of r onto the XY plane. So how do I represent the projection of r on the XY plane?
S d phi.
So you can imagine,
R sine
I'm sorry?
R sine theta.
Yes, r sine theta, excellent. This is the projection, this is actually a 90-degree angle. And you can see these lengths, use a different color. This blue length is the same as this, which is r sine theta. Okay, so I found the other one is r sine theta times d phi. So putting everything together, d area 1 is going to be r d theta times r sine theta d phi, which is r squared sine theta d theta d phi. Okay, so now I got the magnitude. I just need the direction of A1. The direction of A1, you have this balloon, right? And the direction is pointing perpendicular to the surface of the balloon. Is radially outward. And I'm gonna put R hat to represent the direction. Is radially outward. So that is my area. I want you to check at home that if I integrate this area, should I get the surface of a sphere? I should. So when you do this integration, you should get 4 pi r squared, and double check that if that's true. The other area is much simpler because this is just the sort of a little polar, is a little patch on the polar coordinates. And I know you know how to do this. This side is in the radial direction, it's going just to be dr. And this side is arc, which is r d phi. So my dA2 is r dr d phi. It's in the theta hat direction. Now you might wonder, because I'm here, I'm talking about a specific location on XY plane, so that my R now is purely in the XY plane. That's why you can see the R hat in this particular direction is on the XY plane. At a different location, my R hat has a different direction. So this only works if you're talking about the XY plane. Now, if you integrate it, of course, you should simply just get pi r squared because you're talking about the total area of the circle, of a circle. But the important one that we use a lot is this guy. It comes up a lot in our calculation. So I wanted to emphasize how to represent the spherical little patch on the balloon. Okay, having said a lot of that, let's actually now move on to the Dirac delta function. Before we throw in a sort of looks irrelevant topic, I want to be able to provide us with a motivation. So why all of a sudden you want to talk to us about Dirac delta function is there's actually needs such a function because we have a paradox we need to resolve. So let's look at the paradox together. There's a much better graph that is in my slides. You guys can look at this graph later when I upload it. It's better than my drawings. Okay, so here I want to present you with a paradox. Imagine I have a point charge, and we're very familiar with the electric field of a point charge is kq over r squared. That's pointing in the r hat direction, radially outward for a little point charge, right? Never mind the constants, we're just gonna focus on the actual 1 over r squared r hat here because these are just constants. I'm gonna rewrite that vector using 1 over r squared r hat, calling it v, a v vector field. But you know that it's really physically representing something like a point charge, like an E field. Okay? Mathematically, imagine you have something like this, and I'm going to take the divergence of it. In the flyleaf of your Griffiths, so simply just open up your book. You will see a lot of equations that we a lot of times refer to your book and use. Or you can find this in your textbook, that's equation 1.71, that tells you how to represent this divergence in the spherical coordinates. It's already given. So let's say we follow the book. We're just going to do our divergence. So it's ddr, taking derivative with respect to r variable on the r component of this vector. 1 over r sine theta dd theta of sine theta v theta plus 1 over r sine theta d v phi d phi. So by applying this equation with this one given, you can see it's purely in the r hat direction. So v has only vr, which is 1 over r squared. All the other components are 0. It doesn't have any. So I'm going to plug it in. Of course, this is 0, this is 0. I end up with, well, it's actually easy to calculate because v and r component is 1 over r squared. And you can see this is 1. You take a derivative with respect to a constant 1, you get 0, okay? That's straightforward. I get a 0 divergence. So why is there a problem? We realize using the divergence theorem, it's telling me if I integrate this vector over a surface, it should be equivalent to the divergence of this vector over a volume. Volume is defined by this closed surface. So if I integrate over this vector, dA, now that's why we wanted to talk to you about how to represent this dA area, because we now have to write it out. Okay, so on the particular, given a particular length, you can see your R is actually fixed, right? You're on the particular radius. Your R is not a variable going in and out, it's a fixed radius. So I'm going to represent my dA using capital R squared sine theta d phi. And my V, of course, is given at this particular length is 1 over R squared. And you can see V is in R hat. The area is in R hat. So dot product, get rid of the R hat. I get a scalar. So what does this expression looks like? So I get an integration of sine theta d phi, and theta is going from 0 to pi, and phi is going from 0 to 2 pi. You can see that gives me 4 pi. You can work out the details later. Don't worry too much about this process. You can verify the math later. But the point is, you can see that I just found the divergence to be 0. So this is 0. So this should be 0. However, I get a non-zero flux. So what is going on? I know, is there something wrong with the divergence theorem, or is there something wrong with the operation, the calculation we did? So this is the paradox. How do we resolve the paradox? First of all, I want to ask anybody would care to share their thoughts on where the paradox come from, where the problem arise. What do you think?
Well, if we're talking about something that is diverging, when we calculated in spherical, we found that it wasn't diverging at all. However, if we calculated the flux, we found that there was some fluid or substance that was moving through our area. So there's a contradiction in the two results.
Mm-hmm. Yes. So during this process, in this calculation, from here to here, where do you think the problem might come from?
When R equals 0, you're dividing by 0.
When R equals 0, there is a problem indeed. Here, when I do the integration, I'm including an entire space. So I'm definitely enclosing the R equals 0 point. However, when R equals 0, this expression needs to be treated carefully because it will blow up at the location of R equals 0. So we kind of hand waved it by canceling 1 over R squared with R squared. So the R equals 0 doesn't enter into the picture here, but it doesn't mean we can ignore that point. This calculation is only valid at R is not to equal 0 point. So everything else about this calculation is valid except the origin. So the origin has a really bizarre behavior that this V is approaching infinity at R equals 0, and V, when R goes to infinity, this V equals 0 because it's 1 over R squared dependence. So we want to be able to define a function that can capture this feature. So that is the motivation of defining something called Dirac delta function.
Dr. Ryan, why would you have a potential that goes to infinity at the origin?
It's not a potential. I use the V to represent it, but it's just some kind of variable V.
Okay.
Net,
Okay.
if I had said F. Sorry for the choice of coordinates. So,
So
I'm
then
fine. I'm sorry.
Dr. Small talked about the Dirac delta function. I've just been obsessed with it ever since. Is it really just a mathematical convention?
Yes, it's sort of a very abstract thing. It's a mathematical function that we use that can help us understand these or work with our problems a bit better.
Okay. All right. Thank you.
Yes, the calculation is actually really cool. You're right. If we looking at a Dirac delta function, a one-dimensional, I'm going to define delta x to be 0 if x is not 0, but delta x is infinity if we're looking at x equals 0. So you see it blows up here at equals 0, but everything else it's 0. You can see we can't really actually draw it because it's infinity. We can never really draw infinity, right? So we're just going to draw the best we can. This is our delta function. And when you integrate from negative infinity to infinity, we define this integration to be 1. So because of these features, it can be used exactly to describe the behavior of the field that we were looking at earlier. And now before we do that, let's explore a little bit further with the Dirac delta function and do some practice with it before we use it. So you can see that if I integrate the Dirac delta function with another function f, something else, you can see that it will make this calculation quite simple because delta x is 0 everywhere else except at the origin. So your fx can have all kinds of different numbers at different locations, but it's only going to care about the x equals 0 point because everywhere else is 0. So it's going to be f0 times negative infinity to infinity delta x dx. Why only here matters because everywhere else, when x is not 0, delta x is 0. So you don't need to multiply that by f of x, which is not 0. So it's picking out this particular point. And you can see this is 1, as we defined earlier. So this integration looks very complicated. It's simply just going to be f0. Now, if your 0 is within your integration limits, in this case, it is from negative infinity to infinity. However, if I integrate from, let's say, 2 to infinity, fx delta x, what would I get? You can
Is
see
0.
Going to be 0? Yeah.
because everywhere here in this integration limits, delta x is 0, so it doesn't matter what fx is. So it's going to be just 0. Of course, you can move your delta function along the axis. If you have delta x minus a, it will be 0 if x is not equal to a. It will be infinity if x equal to a. You simply just, you're just changing your coordinates. This is nothing fancy. And likewise, when you integrate it over area under the curve is still 1. Of course, you should include x equals a in your integration. Fx delta x minus a is just picking out x equals a point. It's going to be fa in this case. All right, so that's a little bit about this function. I have 2 exercises for you to do real quick. So take a look at this. A piece of paper, let's work on it. I'll give you guys a couple minutes to work on it, and then let's look at it together. So go ahead and work out these 2 integrations. Okay? Let's take a look at the first one together. So anybody would like to share with us how they did the calculation for the first integration?
I defined, or I found what a was and then plugged it into x cubed.
Okay. So what is the result that you got?
I got 8.
8, very good. It's kicking out x equals 2. And is 2 inside my integration limits?
Yes.
Yes, it is. So it's going to be simply at x equals 2, so it's going to be 8. Very good. The second one?
It equals 0.
Yeah, equals 0. Very good. It's going to want us to pick out x equals -1, but we don't have that in our limits, so it's going to be 0. Very good. Okay. So what about this question? We have talked about how to calculate it. We haven't really quite talked about the units of delta function, and does it have units? We need to know the units in order to know how to use it in physics, right? So what are the units for delta x? If x is measured in meters, I will let you discuss in your group for a couple minutes before I bring everybody back. So when you see the invites, just accept and then join the breakout rooms.
I think it is inverse meters, just from, I forget where I read it or which page I read it, but I think that's what I remember seeing.
Yeah, I remember doing it when we were working with the charge per volume density, and that's what I remember it from.
Inverse. So if it's in meters, then it'd be 1/meters.
Okay, I get pretty much all the votes now. Any last minute vote before I close the poll? Okay, let's take a look together. Okay, it seems like the biggest disagreement is whether it has a unit or does it have no units, which is dimensionless. Now, it seems to that majority of you all agree if it does have a unit, it has to be a 1 over length. So can anybody tell us how do they figure out the unit of delta, whether it's unitless or it has a unit, which is 1 over meter? Where can we find something, an expression we have worked out in the notes that is helpful?
Yeah, in the pre-flight, you asked us to an object, and you said it was some constant times the Dirac delta.
Okay.
You know that charge density per meter, what is it, coulombs per meter? Then you know that the Dirac delta function has
I see.
Inverse meter.
I see. So in order for it to represent the charge density properly, and it has to carry the correct units, proper units, and you work it out to be 1 over meter. Yes, indeed. Without having to use it to, before we know that we can actually use it to represent a physical quantity, we need to figure out, does it really have a unit that we need? One thing that can help us is this integration we looked at earlier, is that integral of delta x dx in 1 is a constant. So this side is unit dimensionless. And here you can see this one, if x is the length, so this gives us a meter quantity, right, unit. So in order for them to multiply to give us 1, this one has to be 1 over meter, 1 over length. So yes, indeed, D is correct. And you can see that here, this is 1 dimension. To describe something in space, we need all 3 dimensions. So to be more broadly, to resolve our paradox, and don't forget we still have that paradox hanging at the back of our head, I'm just going to define the 3D delta function, and then we can use it to see how that can help us. So a 3D delta function is simply going to be delta x times delta y times delta z, because it's going to define a point in space. In 1 dimension, x equals 0 is enough to figure out the fixed point. But in space, it's not enough. You need x equals 0, y equals 0, z equals 0 to define a particular point in space, which is our origin. So this is simply telling us at this location, you have an infinity. Everywhere else, you have 0. That's the 3D delta function. Now, of course, if you integrate it over all space with some other function, you're just going to pick out this particular location. So let's see how it's going to help us resolve the paradox by now having the tool of delta functions. You can see the behavior of this 1 over r squared r hat is 0 everywhere. The divergence is 0, we have just calculated, except at r equals 0. And the divergence of this is probably not 0 at r equals 0. So if we rewrite, if we use a delta function to represent this divergence, times a constant, you need a constant, you can see this paradox actually get resolved beautifully. Because now, if you integrate over all space, that's what we did earlier, we get 4 pi. And divergence theorem saying it should give me the same result if I do the divergence of something over all space with a volume. So here, I wrote it in terms of delta function. You get the integration of a delta function over all space and that is 1, right? So you get 4 pi. And now they actually work out if you represent your vector using a delta function. So likewise, you probably already figured out E field can be represented using the 3-dimensional delta functions, describing that the divergence of E is 0 everywhere else except at the origin. So let's take a look at a few more questions. So this one, I think you probably already know. I'm not going to send you to breakout rooms, but we can vote right here. By looking at the units of the 3-dimensional delta functions is if R here, okay, it's describing a position in space that's represented by R vector. And what are the units for the 3-dimensional delta function? Okay, any last minute vote? Okay, I'm going to close end the poll right now. Okay, seems like we all, most of us are in agreement here in terms of the units. I would say if we only look at R, it can be confusing because, okay, if R is in meters, maybe I'm looking at 1/meter. But let's not forget, it's a 3-dimensional delta function. In order for it to work out, in order for this to be 1, we really need to be, you're right, 1/unit length cubed, which is 1/meter cubed. Because if you expand this expression, you're really doing an integration from -infinity to infinity. You've got 3 of them for x and y and z, dx, dy, and dz to be 1, right? So each of them is a meter, so this has to be 1/meter cubed. Excellent, very good. So this expression right here, I want to make a note of this, that more generally, if we're doing the script R, this still follows So instead of just by looking at a particular vector where you have your source in the origin, you can move your source somewhere else, but instead looking at R, script R, and this expression also works. Okay, so it's something more general if your source is no longer at the origin, but at some random place. Let's take a look at a few more questions, and I want to, before we go, talk about a pre-flight that you have already done. So here is an example of when you have a source that is not at the origin, is somewhere in space, a little charge Q. How do I represent the charge density in all space? Now I do need the direct delta function to represent this physical quantity. So which one of these, or maybe more than one of these, is true? I'll give you maybe a minute or a minute and a half in your breakout rooms, okay? So 1 second. If you need to take a screenshot, you can take a screenshot of that before you go to the breakout rooms.
Is there any way that you can assign me to breakout room? I had to leave and come back because my sound was gone again.
Yes, yes, absolutely.
Thank you.
Any thoughts here?
I forgot to take a screenshot, so I'm pulling it up on Blackboard.
Oh, okay. I don't know if I posted there yet. I can share my screen with you.
Oh, okay. Forgive me if I mute myself. I have really bad wisdom teeth pain right now, so.
No problem. So how do you represent the charge density if you're looking at a random point in space? So the charge density, we can describe the behavior by words. This charge, we have a non-zero charge density at the location of the charge, right? But wherever you don't have the charge, wherever else, you have a zero density because the charge is not there. So which one of these delta functions do you think tells us that information? Everywhere else except where the charge is zero.
I believe if I remember correctly from the reading, it was C, where the R would be A in the formula from the book.
So this describes wherever, when your field is at the location of R equals capital R, is going to be non-zero everywhere else except that point is zero. Yes, that does seem to represent what I want. Indeed, I will actually have to close the rooms, bring everybody together, and we can all talk about it when we meet. As you come back, please put in your votes.
Professor? Yes. I can't see the voting window.
Oh, you mean you cannot put in your vote?
Yeah.
Maybe you have closed it. I think there's
okay.
close, you can open it up again. Okay, just 10 more seconds. Let's finish the voting. I do want to talk about the pre-flights before we leave today. Okay, I'm going to end the poll. It seems like the majority of us think, yes, C is correct. Some of you think D is also correct. So maybe we put our wisdom together, we get one of these is correct. So yes, C is correct. You can see that the density is 0 everywhere else except where the charge is, right? That's what the point of have a charge density. You no longer have the charge density everywhere else is 0, but at the location of the point. So what is the charge density at the location of the point charge? It's non-zero. Is it some of finite number or is it infinity?
Yes. It's a finite number.
Okay, what is that finite number?
Rho, like the magnitude of rho.
Yes, we represent it using rho, and now we are giving Q, right, is a charge. So charge density, volume density is Coulomb, the charge over volume. So if I'm confined to one point of the space, you can see that the volume is so tiny. I'm actually looking at the volume density to be pretty much infinity at that location of the charge. So to describe that behavior precisely, a delta function can describe that behavior. It's infinity at r equals r, and it is 0 at r is not equal to. So C is correct. How about D? Does D give me the same amount of information, or is D different from C? Is delta function an even or odd function?
It's an odd function.
Delta negative x is equal to delta x. It all telling me the same information about x equals 0. You have infinity, x equals not 0. You have 0. So it's an even function in the sense a negative x gives me the same value as x x. So this also telling me there's a particular point in space that matters is when r equals r. So it gives me the same information. I know it's not how we usually want to write it. We write it this way, but this is also correct. So C and D are both correct because there are more than one of these. That's correct. So E is correct. So before you leave, I want to take a look at the pre-flight questions. First one, you have a volume charge density that's given by this. Okay, so what are the units of the constant C? Let's do it together. Now, a volume density has to be Coulomb over meter cube. Okay, that's physically what we know. So what C has to be in order for this to be true, and delta function here is 1 over meter, another delta function is 1 over meter, so that this constant has to be Coulomb over meter. So this must be giving me some kind of line charge density right here. Okay, and then describing words, what physical situation this charge density represents. Okay, so it is representing, first of all, I have a charge, line charge, and it is at certain location. And where is this line charge located? What do you think? Everywhere in space, we got density of 0 except at x equals, z equals.
X equals 1.
Is 1, z equals 0. Very good. So here I'm representing a line charge that is located at x equals 1 and z equals 0. So the reason that we need such a delta function to represent it is because we are giving a line charge. We have to represent a volume charge. So we have to introduce the delta function. Okay, so you have a line charge right here. Lambda is exactly represented by the constant c. So you got a line charge running through at x equals 0, z equals x equals 1, z equals 0. So this is my physical representation. And the next one, write a formula for the volume density for this location. Now I need Q, of course, but it's located at where? X equals x naught, y at y naught, and z at z naught. Because only at the location of this location I have the charge. Everywhere else is 0. And you can see that it's a delta function for volume charge density because I'm representing a particular point charge in space and looking at the volume charge density. So likewise, now if you have a surface charge density and if you wanted to represent volume density, you must have some kind of delta function right here. Now, if I have a z minus 2, which means I am giving a surface charge right here at z equals 2, I must have a sphere of some charge on the surface, and that's given me by delta, a sigma right here. Okay, so that's all for today. I have posted my office hour time on Blackboard. Take a look at that, and you have all done your great job on the pre-files, very good. And we have a homework due this Friday. You submit it in the weekly folders directly online. Okay, all right, see you everybody. I'll see you on Wednesday.
Yeah.
Thank you, Dr. Ryan.
Thank you.
Thank you, Doctor.
Thanks.
Thank you. Thank you.
Thank you.
Thank you, bye.